Okay, just picture this for a second. A single photon of light, a tiny speck of energy that started its journey before our own planet Earth was even a thing. It's been traveling for over 13 times billion years, zipping across a universe that's been stretching and growing the whole time. And that epic journey is finally over. It's been caught by this incredible machine we built, the James Webb Space Telescope. This isn't just a telescope, it's our golden eye on the very dawn of time.
And you know, this quote from Neil deGrasse Tyson, it just hits the nail on the head. It's the perfect mindset for what Webb is all about. We're not just out there looking for answers we think we already know. No, we are peering into this vast, mysterious cosmos, and we are totally prepared to be surprised, to have our minds blown, and maybe to challenge everything we thought we knew.
So that leads to the big question, right? How on earth can we actually see back to the very beginning? I mean, it sounds like something straight out of science fiction. But here's the thing. It's not. Not at all. It's all about physics. This telescope is a time machine. And I mean that in the most literal physical sense you can imagine. It was built from the ground up to solve one of the gnarliest challenges in all of astronomy.
All right, so first up, seeing back in time. We're going to get into the physics of ancient light. Let's start with the fundamental science that makes this whole thing possible. And trust me, it's a beautiful, totally mind-bending idea that basically turns every telescope into a window looking out on the past.
Okay, so the key to understanding all of this is something called look-back time. It's pretty straightforward, really. You see, light doesn't travel instantaneously. It has a speed limit, right? The ultimate speed limit. So when Webb captures light from a galaxy that's, say, 13.5 billion light-years away, we're not seeing that galaxy as it looks today. Nope, we're seeing a snapshot of it from 13.5 billion years ago. We're literally looking at the universe when it was just a baby.
But here's where it gets really cool. That ancient light doesn't just travel unchanged. It gets transformed on its epic journey. So step one, a brand new star in the baby universe, spits out some high-energy ultraviolet light. Then, for the next 13+ billion years, the universe itself is expanding. And as the fabric of space stretches, it literally grabs that light wave and stretches it right along with it. So by the time that ancient photon finally gets to Webb's mirror, it's been stretched all the way into the infrared part of the spectrum, which is totally invisible to our eyes.
And that right there is exactly why Webb is such a game changer. Our old friend Hubble, it sees invisible light, like our eyes do, which means it's basically blind to that super stretched out ancient light. It just can't see it. Webb, on the other hand, was designed from day one to see in the infrared. It has infrared vision, so not only can it catch that ancient light, but as a bonus, it can also peer right through those thick cosmic dust clouds that block Hubble's view, letting us see stars being born inside.
All right, section 2, an eye made of gold. We're talking about building an impossible mirror. So you've got this challenge. How in the world do you build a machine that can see invisible ancient light from the edge of time? Well, it all starts with one of the most ridiculously ambitious engineering projects humanity has ever taken on, building a gigantic, perfect mirror.
And when I say giant, I mean wow. The scale here is just immense. Webb's primary mirror is a whopping 6.5 meters across. That's more than double the size of Hubble's, giving it over 6 times the light collecting power. Think about it. If you want to catch the faintest, most distant raindrops, you need a really, really big bucket. It's the same idea here.
But here's the catch. You can't just launch a 6.5-meter wide mirror into space. It's way too big for any rocket. The solution? A masterpiece of what you might call origami engineering. They built the mirror out of 18 separate hexagonal segments. Each one is made from this super lightweight metal called beryllium, and then coated with an incredibly thin layer of pure gold, which, by the way, is perfect for reflecting infrared light. The whole thing was designed to fold up, origami style, just to fit inside the rocket for launch.
Okay, but if you think that's impressive, get ready for the truly mind-boggling part. Once it's in space, those 18 separate segments have to unfold and then align themselves to act like one single, perfectly smooth mirror. And the precision they need to hit? 50 nanometers. So what's 50 nanometers? Okay, picture a single strand of your hair. Now imagine slicing it into 1,000 pieces lengthwise. That's the level of precision we're talking about. And they had to do this in the freezing vacuum of space, 1.5 million kilometers away from any human help. It's just an absolutely staggering feat of engineering. No other way to put it.
All right, next up, engineering the ultimate cold. Because believe it or not, building that mirror was only half the battle. The next challenge? Oh, it was even bigger.
They had to create one of the absolute coldest places in the entire solar system.
So here's the deal. The problem is beautifully simple, actually. Infrared light, well, that's just a fancy word for heat. So if the telescope itself is even a little bit warm, it will start to glow with its own heat, its own infrared light. And that glow would totally blind its super sensitive cameras. It would be like trying to take a photo of a tiny, distant candle while you're standing inside a roaring bonfire. Just not going to happen.
And the solution is probably Webb's most famous feature, that massive 5-layer sunshield. We're talking about something the size of a tennis court. Each layer is thinner than a human hair, made of this special heat-resistant stuff called Kapton. It's designed to block the heat from the sun, the Earth, and the moon. But get this, the process of unfolding it in space had 344 steps where if just one little thing went wrong, one pin, one motor, the entire $10 billion mission would have been toast. The stakes were just unbelievably high.
And did it work? Oh boy, did it work. The results are just staggering. On the side facing the sun, it gets hot enough to boil water. We're talking plus 85 degrees Celsius. But on the other side, where the telescope lives, it's a mind-numbing minus 233 degrees Celsius. That's colder than the surface of Pluto. It's a temperature difference of 1,000,000 to 1. Just insane.
Now, to make this whole sunshield trick work, you can't just put the telescope anywhere. It was sent to a really special place in space called the L2 Lagrange point. Think of it as a gravitational sweet spot, about 1.5 million kilometers from Earth. Out there, the sun, the Earth, and the moon are always lined up behind the telescope. This lets that giant sunshield act like a permanent parasol, constantly blocking their heat and light 24/7.
Okay, moving on. Rewriting cosmic history. What Webb is discovering. So against all odds, the engineering worked flawlessly. The telescope is out there, it's ice cold, it's in focus, and it's catching that ancient light. So now for the really good part, let's talk about what it's actually found and how it is turning our understanding of the early universe completely on its head.
All right, so for decades, the story we told ourselves, based on all our best theories, was this. The very first galaxies to form would be kind of small, messy, and pretty faint. You know, just little clumps of stars slowly getting their act together.
Yeah, but that is not what Webb is seeing at all. It's finding these galaxies way back in the cosmic dawn that are shockingly massive, surprisingly bright, and already beautifully structured. It has thrown a massive wrench into the works, and right now cosmologists are scrambling to figure out what it means. It looks like the universe went from 0 to 60 way faster than anyone ever predicted.
And the records for most distant galaxy ever seen? They just keep getting smashed, way faster than anyone thought possible. I mean, look at this timeline. In 2023, we confirmed a galaxy from when the universe was 325 million years old. By 2024, boom, we're down to 290 million years. That's just 2% of the universe's current age. We're not just inching the frontier back anymore. This is a giant running leap into the unknown.
On top of that, Webb is actually making one of the biggest mysteries in all of physics even weirder. It's called the Hubble tension. Basically, we have two really good ways of measuring how fast the universe is expanding. One method looks at the super early universe, and the other looks at the universe nearby. The problem? They give two different answers. Everyone hoped Webb's amazing precision would solve this, that it would show one side was wrong. But instead, it just confirmed that both measurements are correct, and they still don't match. This is huge. It could be a sign that we need brand new physics, something beyond our standard model of the cosmos.
And all of this leaves us with a huge and kind of thrilling final question. Is the James Webb Space Telescope just confirming the story of our universe that we've been piecing together for 100 years? Or is it actually revealing a massive crack in that story? You know, on one hand, it's showing us what we expected to see. Stars, galaxies, the grand sweep of evolution. But on the other, more fundamental level, with these giant early galaxies and this stubborn Hubble tension, it's showing us things that just don't fit. We built this thing to see the very beginning of our universe. But what if we end up discovering we're part of a completely different story altogether?